Hi, in this video I'm looking at this problem here where we've got a projectile being launched from a horizontal plane with a given speed and at a certain angle, and we want to determine the equations for the trajectory both as a Cartesian equation and vector equation, as well as things like the time of flight, range, and greatest height. Now the best way to tackle these sorts of problems is to start off with drawing a diagram, and in that diagram include a reference frame. So what I mean by the reference frame is basically a set of X and Y axes. So for example, I'm going to call my ground, my horizontal plane, X, and I'm going to call vertically above that ground Y. And I've got this projectile which is being launched from my origin at an angle of 30 degrees with an initial velocity in that direction of 29.4 meters per second. And in fact, I might go and recall this U, not V, because U for initial velocity. So that's the information we're given. And of course, we know when we throw a stone or a projectile of any form, it basically follows a path like that. So we're wanting to now use this information to be able to get the rest of the problem that we need. Now, all of these problems come down from the fact that we got to start with acceleration. So I need to start off with knowing what is the acceleration of my projectile. Now, we might think we're not told about acceleration, but there's always an acceleration downwards due to gravity of 9.8 meters per second. So we're going to call this gravity negative 9.8 meters per second. So there's no horizontal acceleration, but we do have a vertical acceleration of negative 9.8. So it's in the J direction, and we can put on our units and we have our acceleration. Now from here, we can go to velocity. Now velocity, as we know, is given to us by the integral of acceleration with respect to time. So we can integrate our negative 9.8 in the J direction with respect to time to get our velocity vector. So if we do that, there's no horizontal value in this integral, but that means that we're going to have some initial values. We'll get to that later. But our vertical is going to go to negative 9.8 t in the J direction. And the way we're going to do this is we've always got a plus c, but it's a c vector. So my initial velocity is what's going to give me my plus c and complete my velocity vector. And c is given to us by our u over here. Now c is going to be this 29.4 cos the 30 degrees in the horizontal direction and 29.4 sine the 30 degrees in the vertical direction. So that will give us our initial velocity vector. We've got 29 cos 30. Cos 30 is root 3 over 2. So this is going to be 29.4 root 3 over 2i. And sine 30 is just a half. So we're going to have 29.4 times a half j. So then working out these values, we've got c to be, well, half of 29.4 is going to be 14.7. So we have 14.7 root 3i plus 14.7 j meters per second for our initial velocity. So we can go and finish off our velocity equation now, well, our velocity vector, and we're going to have our velocity vector is going to be negative 9.8 tj plus this c that we've just worked out, 14.7 root 3i plus 14.7 j. meters per second. And if we write this out as a full vector by adding the j components, we're going to have 14.7 root 3 I plus 14.7 minus 9.8 t, all for our j, meters per second. So there we go, we've got our velocity, and eventually we're going to get to the trajectory, which is displacement. So now to get our displacement vector, we're going to have to integrate again, because displacement is given to us by the integral of velocity with respect to time. So our displacement is going to be given to us by the integral of this 14.7 root 3I plus 14.7 minus 9.8 t j with respect to time. So if we do our integration, we're going to have 14.7 root 3 t in the I direction and 14.7 t take half, well, we're going to have 9.8 t squared on 2 plus c. And c again is a vector. And that's in our j direction. I almost forgot our j. So now I just need to know what's our initial displacement. And our initial position, because we set up our Cartesian plane to begin with, so we've got our reference point. This point here is 0, 0. So that gives us our c. So that means that c here is 0, 0. So we have that r at the end is just 14.7 root 3 t in the I direction plus 14.7 t minus half of 9.8 is 4.9 t squared in the j direction. And that's our vector equation for our trajectory. So now that I've got the vector equation, it's also asked us to do the Cartesian equation. So I've got this parametric equation. I've just got to turn it into the Cartesian equation. So to do this, we're going to set that x equals 14.7 root 3t and y equals 14.7t minus 4.9t squared, which is what these two parts of our vector equation give us. Get t as the subject, so we're going to have x on 14.7 root 3, and then we can go and substitute that into our y equation. So we get y equals 14.7 times whatever t is, which is x on 14.7 root 3, and minus of 4.9 times x on 14.7 root 3 squared. Simplifying this, we get y equals, well, the 14.7s are going to cancel out, so we're going to have x on root 3 minus, and now we've got this negative 4.9x squared on 14.7 squared times by 3. So dealing with our first part, we've got, let's just rationalize this. So we're going to have x times root 3 on 3 minus off. And if we work out what 4.9 on 14.7 squared times 3 is, then that works out to actually give us only x squared on 132.3. So there we go. We now have the Cartesian equation for our trajectory. And as we can see, it's a quadratic, which makes sense because we quite often know that when we throw something, it follows a parabolic path. So all of that gives us the answer to part A. So now that we've done part A, let's have a look at part B. Time of flight. Everything from here should be easy because now we've got our equations. So time of flight, we've got to think about when does the projectile return to the ground. So to get time of flight, we really want to know at what point does the projectile get there? What is the time when we get to the ground again? And if we think about our equation, I don't know how far away from my origin that is. The horizontal part doesn't help. But my vertical part does, because the point where it reaches there is when it hits the ground. And because it hits there when it hits the ground, that means that it hits the ground when height equals 0. Or in this case, we don't have when height equals 0, we're talking when y equals 0. So what we want to do is just find when the y component equals 0. And if we go to our vector equation, we've got the y component. We know that y equals 14.7t, take 4.9t squared. We had that down here when we sorted out our equation. So I want to solve now when 0 equals 14.7t minus 4.9t squared. And we can factorize this, or you can put it into a calculator, but if we factorize this, we can have 0 equals t outside of 14.7 minus 4.9t. So it occurs when t equals 0, or when 14.7 minus 4.9t equals 0. Well, when t equals 0 makes sense, because that's when we were at our origin. So we just need to solve this one. And so if we work this out, we're going to have negative 4.9t equals negative 14.7. And so t is going to be negative 14.7 divided negative 4.9. And if we chuck that into a calculator, we will get that t equals 3. So we know it happens at 3 seconds or at 0 seconds. So our time of flight is 3 seconds. Let's make that a S. So that's our time of flight. So that's part B. Part C was the range. So this is where we also want to know when we hit the ground, but we want the horizontal component. Now we happen to know that the time when it hits the ground is at 3 seconds. So we can use that with a horizontal displacement. So we hit the ground at t equals 3. So therefore, when x is at 3 seconds, we know that x equals 14.7 root 3t. And so at t equals 3, we've got 14.7 root 3 times by 3. And so if we put that into the calculator, we're going to get approximately, well, in exact values, that turns out to be 44.1 root 3 meters, but an actual numerical decimal will actually be a little bit more useful. So if we put that into a calculator, we get 76.38 meters. So the range is approximately 76.38 meters. And so that's our answer for part C. Now the last part that we need is the greatest height. So greatest height, that's when we are at the apex down here. So we want to know when we're at the apex. So when we know the roots of a parabola, we know that the height is exactly halfway. So if we know that this is 3 seconds and then this is at 0 seconds, we know that halfway occurs at t equals 1.5 seconds. And we've just got to put that into our height equation then. So we can go down and have a look at our height equation again and have a look at part D. So max height is at t equals 1.5 seconds, or as a fraction 3/2 if you want the fraction. And so if we go back to our height equation, we know that our height, y equals 14.7t, take 4.9t squared. And so now we've just got to sub in at t equals 1.5. So we've got y equals 14.7 times 3 over 2 plus 4.9 times 3 over 2 squared. And if we chuck this into a calculator, we get a y of 33.08 meters. So therefore, the greatest height is at 33.08 meters approximately. So there we go. If we want to work out projectile motion and we want the vector and Cartesian equations of the trajectory, we start with acceleration, integrate to get our velocity equation, but we've got to work out our initial velocity, which is given to us by our initial velocity vector, which we just got to work out the horizontal and vertical components using cos and sine. And then to get displacement, we can get our r vector by integrating our velocity vector, and that gives us our vector equation, use it as a parametric equation, and get our Cartesian equation. Then from that, we can answer questions such as time of flight, range, greatest height, just by thinking through things like it hits the ground when height equals 0, so we solve for height equals 0, or when y equals 0, and we get our time of flight. We can do range using that. We can do height using that as well.